All right, this is Chapter 9, Problem 20. We're told that there's a uniform steel beam. It has a mass of 940 kilograms, and resting. It's resting on if you like, two table legs. And on top of that steel beam, there's another miniature, half the size steel beam resting on one side. We're supposed to figure out what is the vertical support on each end, on each table leg, if you like. So let's put a picture here. So you got the one steel beam, and it has a mass of 940 kilograms. And let's see, its overall length is L. And then there's another miniature version, which is half the size. Okay, and then there are some supports here. This M is 1/2 of that. In other words, 470 kilograms. Okay, let's go ahead and label this with the forces that we have. So pressing up, of course, these two legs apply some upward force. Let's call this one F(L) and this one F of R. Okay, left and right. And meanwhile, there's also gravity pulling down on both of these steel beams, effectively at their center of mass. So there's a force of gravity pulling down here. I'm going to call this one F2. I guess that's because I chose this one to be F1. Okay? And the whole thing is at rest. It's not sinking, it's not being launched, it's not rotating, so we're in static equilibrium. That is the main concept that we need here. Concepts that we have. We're looking to get what is FL and FR. So what we have is static equilibrium. Equilibrium. And coming with that, of course, is going to be force and torque. So I'll write that here. Force and torque. Okay. So equation-wise, static equilibrium comes with two conditions. One is that the net force is 0, so I'll write that here. F net is 0, and the other condition is that the net torque is 0. In other words, no launching, no sinking, no sliding left or right, and this is no spinning and no change, if you like, no angular acceleration, no spinning. Okay. What we're also going to need is the actual definition for torque. So torque in general is going to involve a distance from the axis of rotation to where the force is applied. F has a magnitude, the force is a magnitude of F, and there is a sign. I'll write this as sine of phi, and there's a picture corresponding to that. So if this is your axis, and you've got, let's say, like a wrench or something like that, and there is a force being applied like this, force, and this distance is r. The angle made between the force and that radius vector, you can call that phi, if you like, which I have done. That's phi, okay? So your torque is always maximized when that angle is 90 degrees, or pi over 2, and it goes to 0 when the angle is 0 or 180. We have the choice to choose an axis of rotation wherever we like, because the axis of rotation is that place where the place that doesn't spin, that doesn't move. Well, if the whole thing is static, we can pick a place that is most convenient for us. I like to choose something on one of the ends when I do a problem like this. So I'm going to choose my axis of rotation to be here. You can choose anywhere else, and you should get the same answer. So that's going to be our axis. Okay. The net force being 0 tells us that all the forces going up, the sum of them, FL plus FR, should be equal to all the forces pointing down. That's F1 plus F2. Now, F1 plus F2, that's just the sum of the forces of gravity acting on both of these steel beams. If you add that up, using G as 9.8, I should have written that here, I suppose. The force of gravity is mg. I assume by now you know that. F1 plus F2 turns out to be 13,818 newtons, if I didn't screw that up. Okay, let's call this equation number 1. It's not enough to figure out FL or FR separately. We have to use the net torque being equal to 0. Okay, net torque equal to 0. That means, if you like, the clockwise torque minus the counterclockwise torque, or vice versa, if we used a different convention, would add up to 0. That tells you that whatever the clockwise torque is total, it has to be equal in magnitude to whatever the counterclockwise torque is in total. Okay, so if we put our axis here, we know that the force on the left applies no torque because its distance from the axis is 0. By definition, we chose it because it would be simple that way. The distance of F1 from the axis, this is L over 2, L over 4. This distance is L over 4. This distance is L over 2. Let me clean this up slightly. L over 4, and this is L over 2. These things make a torque that goes this way, clockwise. So what we have, keeping in mind that sine of phi, that's 1 because the radius vector pointing this way makes an angle that's 90 degrees with gravity, which points down. It's a nice simple problem. So what we have is an R, L over 4, that's, if you like, the R1, times this force, F1. That's the torque provided by the gravitational force pulling down on a smaller beam, plus the torque provided by the gravitational force pulling down on the bigger beam. That distance is L over 2 times F2. Okay, that's all the torque making the thing want to spin this way, which is clockwise. Yes. On the other side, counterclockwise torque, there's only one thing remaining. The force on the right-hand side, that's the thing trying to make it spin this way, which is counterclockwise. The lever arm, or the radius vector length, if you like, is the full L. And the involved force is Fr. Okay. Again, this sine of phi, you can choose whatever angle is most convenient. It doesn't matter whether it's like this, that's 90 degrees, this is 90 degrees as well. Okay, this is the second equation. You'll notice the actual length doesn't matter, as it shouldn't. They didn't give us any numbers. And F1 and F2, those are things that you can compute. I'm just going to go ahead and put in what they would be. F1 involves the 470 kilograms times the 9.8 meters per second squared. This thing has the 1/2, the 940 kilograms times the 9.8 meters per second squared equal to Fr. When you compute this, what you should find is that Fr is 5757.5 newtons. We'll round this in a bit. Now that you have this, you can put that into this first equation. Now you know Fr and you know what's on the right-hand side. That tells you that Fl is 8060 or so. I think there's a 0.5 in there, newtons. So we're basically there. In the end, we need to round up because we're only given 2 or perhaps 3 significant figures here. Let's call that 2. And so in the end, Fr, we'll write this as 5,800 newtons, and Fl is 8,100 newtons. As a sanity check, we should be able to go back and make sure that the sum of Fl and Fr give us enough force to keep the steel beams suspended.